In R.8 we talk about radicals. So the nth root of a refers to the number that you can raise to the nth power to get a. We usually denote this with exponents, a to the 1 over n. That's because if you took a to the 1 over n and raised it to the nth power, good old laws of exponents would say that when you raise a power to a power, you multiply the exponents. And 1 over n times n is 1. So a to the 1 over n does what the nth root of a is supposed to do. So we use this exponential expression to rewrite that radical guy. Generally, a to the m over n means either the nth root of a to the m, or it means the nth root of a raised to the nth power. That is, if a is positive. You see in a lot of the homework in the instructions that you're supposed to assume that all the variables involved in the problems are positive. That's because working with radicals gets kind of sticky when you allow negative numbers. For instance, you can't take an even root of a negative number, and when you take even roots of positive numbers, there are two different answers. That is, if I ask what is the square root of 9, 9 has two square roots. You know, they're plus and minus 3. But this symbol, by definition, is taken to mean the positive root. So the principal root, the square root of 9 is 3, even though 9 has two square roots. So this refers to the principal square root of 3, the principal square root of 9. If I'm taking an odd root, there's no worry about whether there should be a plus or minus, because every number has exactly one odd root. For instance, if I take the cube root of 27, it's 3, because 3 cubed is 27. Negative 3 cubed is negative 27. So the cube root of negative 27 is negative 3. So anyway, I'm going to write down a couple of laws of exponents, and this is assuming that all the variables involved are positive. There's really just a couple besides this one, and that is the nth root of AB is the same as the nth root of A times the nth root of B. That's because I think that nth roots are really just powers of A. This is AB raised to the power 1 over n. This is a raised to the power 1 over n and b raised to the power 1 over n. The laws of exponents say that if you take a to the 1 over n and b to the 1 over n, that should be the same thing as ab to the 1 over n. We saw this law of exponent a long time ago when the exponents were whole numbers, but it's still true when they're fractions like 1 over n. And similarly, the nth root of a over b is the nth root of a over the nth root of b, assuming that b isn't 0 so that I can have that thing in the denominator. But, warning, you can take the radical of a product or a quotient this way, but not of a sum. The nth root of a plus b does not equal the nth root of a plus the nth root of b. There are a lot of problems in the homework where you have to simplify expressions involving radicals, and I think you can solve many of them the same way. So for instance, if I'm supposed to simplify the cube root of x to the 7th, I write that, I use exponents to help me solve that. I rewrite it in the form x to the 7/3. Now that's an improper fraction. The numerator is bigger than the denominator. So rewrite it as a mixed number, a whole number plus a proper fraction. 7/3 is the same thing as 2 1/3. And good old laws of exponents say that when there's addition there, that's the same thing as multiplying two different powers of x. X squared times x to the 1/3. And x to the 1/3 is the same as the cube root of x. That is, cube root of x to the 7th is the same thing as x squared times cube root of x. Let's try another one. Suppose they want me to simplify the cube root of 208 y to the 11th. I would try to factor the 208. Let's see. 208, that's 2 times 104. That's 2 times 2 times 52. Oh, that's a deck of cards. That's 2 times 2 times 2 times 2 times 13. So what they want me to simplify is the cube root of, let's see, 1, 2, 3, 4, 2 to the 4th times y to the 11th times 13. I treat these prime numbers 2 and 13 just like the x in the previous problem. Let's rewrite all those guys with exponents. That's 2 to the 4/3 times y to the 11/3 times 13 to the 1/3. And rewrite all these fractional exponents, these improper fractions, as mixed numbers. So that's 2 to the power 1 plus 1/3. And 11/3, that's 3 2/3. So that's y to the 3 2/3. And this is just good old 13 to the 1/3. So pull aside the things raised to whole number exponents. That's 2 to the 1 times y cubed. And rewrite the other guys, y to the 2/3, 13 to the 1/3, like that. Now all these exponents are, proper fractions. The denominator is bigger than the numerator. That's supposed to be a denominator of 3, isn't it? So this is 2y cubed. All these guys have denominator of 3, so they're the cube root of 2 times 13 times y squared, or 26y squared. That's about as bad as it can get in those simplify the radical expressions. One of the things they asked me to do in section 5.8 is to rationalize denominators. And let me give you a couple of examples. Let's say I have 2 plus the square root of 5 divided by the square root of 7. To rationalize the denominator means to rewrite the fraction so that there are no radicals in the denominator. It's not something that we really need to do for practical reasons, but it's a good algebra exercise for the things that are coming up in calculus. So to get rid of the radical 7 in the denominator, what I would like to do is make that radical go away. Well, what makes a square root go away? Multiplying by itself. Well, I can't just multiply that denominator by radical 7. That changes the whole fraction. But I can multiply the whole fraction by radical 7 over radical 7. That's just multiplying by 1. So the top is 2 plus radical 5 times the square root of 7. And the bottom is square root of 7 times square root of 7 is 7. I could leave it like that, or I could distribute this radical 7 across this sum in the numerator. I guess that's 2 radical 7 plus radical 5 times radical 7 is the same thing as square root of 35. I don't know, I think either one of these is about equally simple. Now that I did this, I really don't think I needed to. I think that answer was probably just as good. What if this had been, let's say, square root of 5 divided by cube root of 7? What would make the cube root go away? Not squaring it, but cubing it. What I would like to do is multiply by cube root of 7 in the denominator. In order to justify putting that into the denominator, I also have to put it into the numerator. And I got to admit, I think that's kind of silly now the way I wrote it. Cube root of 7 times cube root of 7 is the same thing as the cube root of 49, or the square of the cube root of 7. There are probably simpler ways to write that. But on the top I'll have square root of 5, cube root of 49, I guess, and on the bottom there's just a 7. I could combine these two if I wanted. I'd have to write them, I'd have to write this as 5 to the 1/2 and 49 to the 1/3. You know what, that doesn't really simplify at all. Let's try one more. So how about 1 plus the square root of 7 over 2 minus the square root of 7. Now the thing that gets the radical out of the denominator is to recognize that 2 minus radical 7 is half of the difference of squares formula. If I multiply the denominator by 2 plus the square root of 7, and I'll have to do the numerator the same way to justify doing it, then see the denominator is a square minus a square. It's going to be 2 squared minus radical 7 squared. And on the top I just get some stuff. But the denominator is going to be 4 minus 7, or negative 3. In the top, I probably should FOIL out the top to see what I get. There's going to be, the first term is going to be a 2. The inside and outside terms are going to add up to, let's see, there's 2 radical 7 there, and there's 1 radical 7 there. Altogether that's 3 radical 7s, just like if that radical 7 was an x. And finally, the last term will be radical 7 times radical 7, that's 7. So I guess I have 9 plus 3 radical 7 in the top, and it's being divided by negative 3. Ah, 3 is a factor of the top. I better factor the top before I can cancel a 3. And the top's not been factored because the last operation being performed is that addition. So factor out the common factor of 3 that you see in the top. Now it's safe to cancel the 3's. So I've got 3 plus radical 7 divided by negative 1. To divide something by negative 1 is the same as multiplying it by negative 1. So I'll just multiply that by negative 1 so I can say I'm done.